Among the wide variety of types of combat aircraft, a special, in many ways unique place is occupied by the Specialized Attack Aircraft for Direct Support of Ground Forces AS-130, which is a deep combat modification of the S-130 Hercules transport aircraft, armed with a whole set of powerful artillery guns, directed not forward along the flight path, as is customary on the vast majority of other combat aircraft, but strictly sideways, perpendicular to the direction of flight itself. Airplane. Such a very non-trivial configuration of weapons is due to a fundamentally different from the traditional tactical principle of combat use of this specific type of aircraft. Instead of the standard approach, which involves a short, rapid passage over the target with the subsequent use of weapons and immediate departure, the AS-130 uses a fundamentally different tactic. The aircraft performs a long, stable turn at a certain altitude directly around the ground target, keeping it constantly in the range of its onboard weapons directed strictly to the side for a significant, often very long period of time. Such tactics, known as pylon turn piloting, allow the aircraft crew to carry out extremely accurate, long-term and, importantly, continuous visual observation of a specific ground target using previously discussed optoelectronic sighting systems, if necessary, adjusting the accuracy of the use of onboard weapons in real time throughout the entire period of impact on this specific target. The onboard armament of the AC-130, depending on the specific modification of the aircraft, traditionally includes various combinations of rapid-fire guns of various calibers, and in the most modern modifications, high-precision guided weapons capable of hitting specific, pinpoint ground targets with exceptionally high accuracy with minimal risk of collateral damage to friendly troops or civilians located in close proximity to the target. The exceptional practical value of such a specialized aircraft for direct, long-term fire support of ground forces, especially in conditions of combat operations in populated areas or other complex terrain saturated with various objects, or exceptionally accurate, selective use of weapons with minimal risk of hitting foreign objects is required, made the AS-133 one of the most popular, intensively used types of combat aircraft during a number of military conflicts in recent decades. A significant limitation of such a specialized aircraft is its relatively low speed and very limited maneuverability compared to conventional combat aircraft, as well as its relatively large dimensions and the lack of any significant protection from modern air defense systems, which makes the AS-130 significantly vulnerable in the face of real counteraction from a technically advanced enemy who has modern anti-aircraft missile systems, limiting the practical use of such an aircraft mainly to situations involving relatively weak or completely absent organized air counteraction from the opposing side of the conflict. That is why such aircraft are traditionally used primarily in the dark, making maximum use of the previously discussed capabilities of modern night vision and thermal imaging surveillance systems for covert, most effective detection and subsequent destruction of enemy ground targets with a significantly reduced risk of visual detection of the aircraft itself by means of enemy ground air defense, which are objectively less effective in conditions of complete darkness compared to daytime. Among the many non-standard engineering solutions used in the history of military aviation, the variable sweep wing occupies a special place, a concept that allows the same aircraft to physically change the geometry of its own wing directly in flight, thereby adapting to the fundamentally different, often mutually exclusive requirements of different phases of the mission. The most famous practical implementations of this concept in American military aviation were the previously mentioned F-14 Tomcat carrier-based fighter and the F-111 tactical strike aircraft. The fundamental engineering problem that such a technical solution was intended to solve is the objective, physical contradiction between the requirements optimal for efficient flight at low, subsonic speeds, and the optimal requirements for efficient flight at much higher, supersonic speeds. A relatively wide, maximally deployed wing, providing a significant lifting surface area, is optimal for efficient low-speed flight. It provides sufficient lift at a relatively low airflow speed, which is critical, in particular, for a relatively slow, controlled approach, including the previously mentioned extremely critical landing on the limited deck of an aircraft carrier. However, the same wide wing creates a significant aerodynamic drag, which significantly increases as the flight speed increases, precisely at high, approaching supersonic or already supersonic speeds, which significantly limits the maximum achievable speed of the aircraft and significantly increases fuel consumption precisely in such a high-speed flight mode. The variable sweep wing solves this fundamental contradiction through a special mechanism that physically rotates the wing console relative to the fuselage of the aircraft, from a maximum deployed, almost perpendicular to the fuselage position, optimal for low-speed flight, takeoff and landing, up to a much more swept, significantly deflected back position, which significantly reduces aerodynamic drag precisely at high, supersonic flight speeds. Such a rotary mechanism is a very complex, technically demanding structure, forced to transfer significant mechanical loads from the wing itself to the main fuselage structure precisely through a relatively small, movable hinged attachment point, which significantly complicates the overall design of the airframe and significantly increases its total mass compared to the much simpler, fixed design of a traditional fixed wing. The pilot of such an aircraft, as a rule, was able to either independently, manually adjust a specific wing sweep angle depending on the current phase of flight, or, in certain, most technically advanced modifications of such aircraft, rely on an automatic system that independently calculates and sets the optimal wing sweep angle directly depending on the current flight speed and other relevant parameters determined by the aircraft's onboard computer. Despite the obvious, very significant practical advantages of such a concept in terms of the versatility of the flight characteristics of the aircraft in the widest range of possible flight speeds, significant mechanical complexity, a noticeably increased total mass and, accordingly, a significantly increased cost of production and subsequent maintenance of such a complex rotary mechanism led to the fact that the modern generation of American fighters, including the previously mentioned F-22 and F-35, abandoned such a concept in favor of a much simpler one, a fixed wing, compensating for certain associated limitations with other technical solutions, including the previously discussed concept of a deliberately aerodynamically unstable airframe controlled by a modern fly-by-wire control system. Among the very diverse fleet of specialized military aircraft, there is also a rather unusual, highly specialized category, whose direct combat mission is not direct physical impact on the enemy, but informational and psychological impact through broadcasting specially prepared radio and television programs directly into territory controlled by the enemy, the specialized aircraft EU-130 Commando Solo. This aircraft, also built on the basis of the previously mentioned multi-role transport aircraft C-130 Hercules, is equipped with an exceptionally powerful set of radio and television broadcasting equipment capable of broadcasting specially prepared information content on a wide variety of radio frequencies, including both standard, widespread frequencies of ordinary civilian radio and television broadcasting, and certain specialized military communication frequencies potentially used by directly opposing enemy armed forces. The power of the onboard transmitting equipment of such a specialized aircraft significantly exceeds the power of typical ground-based broadcast stations, which, in combination with the significant flight altitude of the aircraft itself, which significantly expands the effective signal coverage area due to significantly better radio visibility from a high altitude, allows for effective information broadcasting over a very wide area, often completely blocking or at least significantly drowning out the signal of local, enemy-controlled broadcast stations in a given specific territory. The specific content of such specialized broadcasting is very diverse and is determined by the specific strategic and tactical objectives of the current military operation. This may include directly informing the local civilian population about the current military situation and related recommendations for ensuring personal safety, psychological influence directly on the opposing military personnel in order to reduce their morale or encourage them to voluntarily surrender, as well as countering propaganda materials distributed by the enemy himself among the local population or his own armed forces. In addition to the direct broadcast function, such a specialized aircraft is often equipped with additional equipment that allows it to carry out certain forms of electronic counteraction directly to the enemy's communication and broadcasting systems, further complicating effective information counteraction on the part of the opposing side of the conflict throughout the entire period of active use of such a specialized aircraft in a particular region of the conflict. The crew of such an aircraft traditionally includes not only the flight crew itself, which provides direct control of the aircraft itself, but also a significant group of highly specialized specialists in psychological operations and technical support for broadcasting, who are directly responsible for the content and technical quality of the broadcast, which makes such an aircraft, in fact, a full-fledged flying broadcast studio integrated directly into the fuselage of a military transport aircraft. The use of such very non-standard, highly specialized means of information and psychological influence remains relatively little known to the general public, but at the same time it is quite an important element of the general modern military doctrine, clearly demonstrating that real modern military aviation solves a significantly wider range of tasks than exclusively direct physical destruction of enemy targets and manpower, including much less obvious, but at the same time no less strategically significant aspects of information and psychological confrontation within the framework of a modern, complex armed conflict. We have already repeatedly mentioned the landing of personnel and cargo directly from military transport aircraft. But there is a relatively new, technically very advanced category of such airdropping, the Joint Precision Airdrop System, JPADS, which represents a significant technological leap compared to the traditional, much less accurate method of simply freely dropping cargo using conventional, uncontrolled parachute systems. The fundamental problem with traditional, uncontrolled cargo drops is the very significant exposure of the actual landing point of the dropped cargo to wind at various altitudes during the relatively long descent of the cargo on a conventional, uncontrolled parachute, which often leads to a very significant, sometimes reaching several kilometers, deviation of the actual landing point from the originally planned drop point, especially when landing from a sufficiently high altitude in conditions of moderate or strong winds at various altitudes. Such inaccuracy of the traditional landing method creates very significant practical problems. Cargo that has deviated a significant distance from the intended collection point may be inaccessible to friendly ground forces for which this cargo was originally intended, or, even more dangerous, it may end up in territory controlled by the enemy, which necessitates either a very risky additional operation to search and retrieve such deviated cargo, or its complete, irretrievable loss. The JPADS system solves this fundamental problem by equipping the landing cargo with its own autonomous navigation and control system, very similar in general principle of operation to the previously discussed in detail control system for unguided, but GPS-corrected aircraft ammunition of the JDM type, although adapted for the fundamentally different task of precise landing, rather than hitting a specific target. Technically, such a system includes a special module equipped with its own GPS satellite navigation system signal receiver, which determines the current actual location of the descending cargo in real time, as well as a special controlled parachute system, which, as a rule, is not a traditional, simple round parachute, but a much more technically advanced gliding parachute, capable, like a traditional wing parachute used in parachuting, to carry out controlled, directed flight in a specific desired direction through appropriate control of the tension of certain lines of the parachute itself. The onboard computer of such a system continuously, throughout the entire process of dropping the load, compares the current actual location of the load, determined by GPS, with a predetermined target landing point, automatically making the necessary adjustments to the parachute control to bring the load to the pre-planned, desired landing point as accurately as possible, compensating for the actual effects of the wind, instead of the inevitable, significant deviation characteristic of the traditional, completely uncontrollable method of landing. The practical accuracy of such a modern precision landing system is significantly, often an order of magnitude higher than the accuracy of the traditional, unguided landing method, which makes it possible to supply remote, hard-to-reach units or isolated settlements much more efficiently and, importantly, much more safely, minimizing both the risk of losing the cargo being dropped due to a significant deviation from the intended landing point, and, no less important, significantly expanding the possible height of the actual landing itself. Cargo drop, since the carrier aircraft no longer needs to risk descending to the relatively low altitude traditionally required to achieve acceptable accuracy when using the much less advanced, completely uncontrollable method of landing. We have already examined in detail the general principle of guidance of modern air-to-air missiles. But there is an important concept that largely determines the actual tactics of air combat, known as the zone of inevitable destruction, no escape zone, which characterizes a specific, very specific area of space relative to the attacking aircraft, within which the attack target has practically no real physical ability to successfully evade a missile that has already been fired at it, regardless of the evasive maneuvers undertaken by the pilot of the attacked aircraft. The fundamental physical logic of this concept is that a modern air-to-air missile, like any other physical object, has an objectively limited supply of its own kinetic energy, determined primarily by the fuel supply of its own rocket engine, as well as the initial speed and altitude obtained at the moment of direct launch of the missile from the attacking aircraft. If the target being attacked is located at a relatively short distance from the attacking aircraft at the time the missile is launched, the missile retains a very significant reserve of its own kinetic energy throughout the entire subsequent flight to the target, which allows it to effectively, with a significant margin of maneuverability, follow any, the most energetic evasive maneuvers undertaken by the pilot of the attacked aircraft, almost guaranteed to overtake and hit the target, regardless of the specific nature of such evasive maneuvers. However, as the initial missile launch distance increases relative to the target being attacked, and also depending on the specific geometry of the attack, for example, when a missile is launched not strictly towards the target, but at a certain, less favorable angle, the missile is forced to spend a significantly larger part of its own limited supply of kinetic energy simply to achieve the target itself, leaving, accordingly, a significantly smaller supply of available energy directly for effective maneuvering following possible evasive maneuvers of the attack target already in the final section of its flight, which potentially provides an experienced pilot of an attacked aircraft with a real, quite practical chance of successfully evading a similar, much less energetic attacking missile at this stage of the flight. That is why modern fighter pilots, equipped with an appropriate onboard system that displays the approximate boundary of such a zone of inevitable destruction relative to the current relative position of their own aircraft and a potential enemy, strive, if possible, to initiate the launch of their own missile weapons from a distance that ensures that the specific target being attacked is located within such a zone of inevitable destruction, since launching a missile from a much greater distance, with the technical range of the missile itself being formally maintained, significantly increases the real practical chance of the attacked enemy being successful evading a similar missile fired from a much greater distance. This concept also significantly determines the general tactics of defensive maneuvering of the attacked aircraft, a timely, fastest response directly to the very fact of detecting the launch of an enemy missile, the technical means of detection of which we have already discussed in detail in one of the previous parts of this material, through an immediate, energetic maneuver aimed at the fastest possible exit from the potential zone of inevitable destruction relative to a specific attacking missile, often represents a significantly more realistic, practically achievable tactical task compared to an attempt to purely reactive, belated evasion directly at the very final stage of the flight of an already closely approaching attacking missile that still retained a significant reserve of energy. We have already examined in detail the general principle of aerial refueling using specialized tanker aircraft. But there is an alternative, much smaller scale, but very practically valuable concept in certain tactical situations, the so-called buddy refueling, in which the role of an improvised, limited-capacity refueling tanker is performed not by a specialized tanker aircraft, but by an ordinary tactical fighter or attack aircraft, equipped with a special suspended refueling container. Such a specialized outboard container, installed on one of the external hardpoints of a conventional combat aircraft instead of traditional weapons or an outboard fuel tank, contains inside a compact version of the refueling equipment, including its own supply of fuel taken from the internal tanks of the carrier aircraft of this container, as well as the fuel supply mechanism itself, implemented, as a rule, using the previously discussed in detail flexible hose system with a receiving funnel. Much more compact and technically simpler compared to a complex rigid boom system that requires a much larger specialized tanker aircraft to accommodate it. The key practical advantage of such a concept lies in significantly increased tactical flexibility. A conventional squadron of tactical fighters, without having its own specialized refueling aircraft within the framework of a given specific combat sortie, nevertheless gets the opportunity to carry out limited, but often quite sufficient to perform a specific tactical task, refueling of one or more aircraft of the group directly by one of the members of the same group, temporarily allocated and appropriately technically equipped to carry out such a task. Auxiliary function. Such a concept is especially valuable in carrier-based conditions, where the number of available specialized carrier-based refueling aircraft is objectively very limited by the space of the aircraft carrier itself, while the ability of any standard, full-time carrier-based fighter, if necessary, to temporarily take over the limited function of refueling neighboring aircraft of the group significantly increases the overall tactical flexibility of the entire air wing without the need for an additional specialized refueling aircraft, which takes up valuable space in the overall composition of an already limited air wing. A significant practical limitation of such a concept is the inherently significantly smaller volume of available fuel available for transfer through such a compact outboard refueling container, compared to the significantly larger volume of fuel available on board a dedicated tanker aircraft, which makes such buddy refueling an effective solution primarily for relatively small, limited refueling, sufficient, for example, for the safe return of an aircraft with significantly insufficient fuel remaining to the nearest suitable airfield, but objectively insufficient to significantly extend the total range or flight duration of the entire group of aircraft as part of a prolonged combat operation. However, the very fundamental possibility of such auxiliary, buddy refueling remains a very valuable additional tactical tool, significantly increasing the overall operational flexibility and, importantly, the overall safety of tactical aviation flights in a number of specific practical situations where full support of a specialized refueling aircraft for one reason or another is unavailable at a specific moment in the current combat mission. We have already discussed in detail the modern role of airborne early warning and control aircraft, such as AWACS, in providing general information awareness and coordination of modern air combat. But long before the advent of such a technically very advanced air control system, the essentially similar function of guiding interceptor fighters to enemy air targets was performed by a much older, ground-based control system, known as the Ground Controlled Interception (GCI) system. The operating principle of such a much earlier system was based on the use of stationary or, in certain cases, relatively mobile ground-based radar stations that monitor the current air situation within their technical detection range, followed by direct voice transmission of the corresponding tactical instructions to the crew of the duty fighter interceptor via standard radio communications, ensuring the necessary guidance of the interceptor directly at the detected enemy air target. The operator of the ground guidance station, observing the current relative position of both the interceptor and the detected enemy target directly on the screen of his own radar indicator, sequentially transmitted to the interceptor pilot precise voice instructions regarding the required course, altitude, and flight speed, gradually, step by step, bringing the interceptor into a position that provided the possibility of direct visual or, in the case of the presence of appropriate onboard equipment, independent radar detection of the target using the interceptor's own technical means, sufficient for subsequent independent completion attacks. Such a system, for all its relative technical simplicity compared to modern air control systems, played an extremely important historical role, in particular during the previously mentioned air battles in the skies over Korea, and also, somewhat later, in the overall air defense system of both opposing sides of the Cold War, providing a critical ability for the timely detection and subsequent effective interception of potentially threatening enemy air targets long before the advent of much more technically advanced air systems management. A significant fundamental limitation of such a completely ground-based guidance system was the objective physical limitation of the operating range of directly ground-based radar stations, which are significantly inferior in their effective detection range to much more advanced modern airborne radar surveillance systems located at a sufficiently high altitude and, accordingly, have significantly better radio visibility compared to any, even technically very advanced ground-based radar station, whose effective detection range of low-flying targets is inevitably limited by itself. The curvature of the Earth's surface and the features of the specific terrain in the area where such a station is located. It is this fundamental limitation, along with the significantly increased overall complexity and intensity of modern air combat, which requires significantly more complete, comprehensive and operational information awareness compared to the relatively limited capabilities of a separate ground-based guidance station, that served as one of the key reasons for the subsequent transition to a much more technically advanced air combat control system based on specialized early warning aircraft, which we have already discussed in detail earlier, although certain elements and principles, initially developed precisely within the framework of an older, ground-based guidance system, continue to be used to a certain, limited extent, within the framework of a modern, much more technically advanced control system for modern air combat. The end of a long, often many-year flying career of a military pilot is traditionally accompanied by a special, very firmly established ceremonial tradition in the military aviation environment, the so-called farewell flight, fini flight, which is the last official flight of a particular pilot on a combat aircraft immediately before his final transition to an exclusively ground-based position or the complete completion of military service. This tradition, which originated in the first decades of the formation of military aviation as such, includes a number of specific, highly symbolic ritual elements, varying to a certain extent depending on the specific country, branch of troops and even a specific unit, but invariably retaining a common fundamental idea, a solemn, emotionally significant celebration of the completion of an important stage of his personal and professional life, often determining a significant part of the professional identity of a particular person. The farewell flight itself, as a rule, includes certain special elements that distinguish it from a regular, ordinary combat or training flight. Often such a flight includes a symbolic flight over some personally significant place for a particular pilot, be it his home, or, for military personnel of certain branches of the military, a symbolic final flight over the territory of his own airbase at the minimum permissible altitude, attracting the attention of a significant part of the base personnel, who are aware in advance of the upcoming farewell the flight of a specific respected colleague. Upon the immediate return and successful landing of the aircraft piloted as part of such a farewell flight, a special, very colorful and often quite noisy ritual ceremony traditionally follows directly at the aircraft's parking spot. Fellow soldiers, often including a significant part of the unit's personnel, pour water from hoses or specially prepared buckets over the pilot who has just left the cockpit, which symbolizes a kind of ritual washing on the occasion of a significant, important life transition, in many ways similar in its symbolic function to certain other professional rituals of this kind, widespread in a wide variety of professional communities not directly related to military aviation. A significant additional element of such a tradition is often the subsequent ceremonial presentation of a certain memorable insignia or a symbolic gift from colleagues to the pilot finishing his flight career, as well as, often, solemn speeches and toasts by colleagues in the command of the unit, often with a fair amount of specific humor characteristic of the military aviation environment, speeches and toasts, marking specific, most memorable achievements and episodes of the long flying career of the pilot ending his service. Such a tradition, deeply rooted in military aviation culture, along with other elements of this specific professional culture already discussed in detail, squadron emblems, personal call signs and a specialized code of brevity in radio communications, clearly demonstrates that special, very strong social and emotional fabric of the professional community of military pilots, where significant life and career milestones are traditionally celebrated through special, deeply symbolic rituals, significantly going beyond the purely formal, official procedure for completing military service or moving to a new position. We have already repeatedly mentioned the general physiological threat of depressurization of an aircraft cabin at high altitude in the context of various aspects of high-altitude flights. But the specific, very specific phenomenon of a sudden, rapid loss of pressure in a pressurized aircraft cabin, the so-called explosive, or rapid decompression, explosive decompression, deserves a separate, more detailed consideration precisely as an independent physical and physiological phenomenon. Explosive decompression occurs in a situation in which the pressurized shell of an aircraft cabin, which maintains a significantly higher internal pressure compared to the much more rarefied atmosphere outside at high flight altitudes, suddenly, almost instantly, loses its own tightness due to serious mechanical damage, for example, as a result of combat damage to the fuselage, structural destruction of the cabin glazing, or other similar serious structural damage in its consequences. The physical processes occurring in such a situation unfold with exceptional speed, often barely perceived by human consciousness. A significant difference in pressure between the internal volume of the cabin and the much more rarefied external atmosphere leads to a rapid, explosive release of air from the cabin to the outside, often accompanied by a powerful, short-term airflow, physically capable of tearing loose objects located inside the cabin, and even, in certain, most serious cases, posing an immediate physical danger to people in the cabin. An equally significant, often more insidious consequence of such rapid decompression is the associated sharp, almost instantaneous drop in temperature inside the cabin, caused by the thermodynamic effect of adiabatic expansion of gas known from general physics. Air, rapidly expanding due to a sharp drop in pressure, is just as rapidly cooled, which can lead to a drop in temperature inside the cabin by tens of degrees literally in a fraction of a second, creating an additional serious physiological threat for people inside in addition to the direct threat already mentioned earlier, oxygen starvation due to a sharp drop in pressure. As such, it is the prospect of such a rapid, potentially deadly decompression that explains the previously discussed in detail the need to constantly wear oxygen masks or, in the case of high-altitude reconnaissance officers like U-2 and Blackbird, full-fledged high-altitude spacesuits, since the time objectively available to a person for an effective reaction to such a rapidly developing emergency situation, in the absence of such constant protection, can be calculated in literally a matter of seconds, objectively insufficient for a conscious, purposeful reaction without pre-applied protective equipment. Modern military aircraft are structurally designed taking into account the fundamental possibility of such an emergency situation, including certain technical solutions aimed at minimizing the most serious, potentially traumatic physical consequences of the very moment of rapid decompression, as well as automatic systems that immediately send an appropriate emergency signal to the crew and, often, automatically initiate the supply of additional oxygen through a previously discussed oxygen supply system immediately at the moment the onboard sensors detect such a sharp, emergency drop in pressure inside the cabin, which significantly increases the real chances of the crew to successfully overcome such an objectively very dangerous and rapidly developing emergency situation. We have already examined in detail both the general principle of laser target designation and the role of modern aiming containers in the independent targeting of onboard weapons of a particular aircraft. But there is also a very valuable concept in certain tactical situations of the so-called buddy laser target designation, buddy lasering, in which one aircraft carries out direct laser target designation of a specific ground target, while the actual use of laser-guided weapons is carried out by a fundamentally different, separate aircraft. The practical tactical value of such a division of functions between two different aircraft is very significant in a number of specific combat situations. For example, an aircraft that directly carries out long-term laser target designation of a specific ground target is forced for a certain, sometimes very significant time, to maintain a fairly stable, predictable position relative to this target, ensuring the necessary accuracy of continuous laser illumination, which potentially makes such a target designator aircraft much more vulnerable to possible counteraction from enemy ground-based air defense systems compared to a much more maneuverable, less predictable flight path by an aircraft directly carrying out the release of the guided munition itself. The division of such functions between two different aircraft allows, accordingly, to optimize the tactics of each of them for a specific task. A target designator aircraft can, for example, remain at a relatively safe distance or altitude that is optimal precisely for a stable, long-term hold of the laser beam on the target, while the attack aircraft itself gets the opportunity to use its own weapons using a much more flexible, less predictable approach tactic, minimizing its own vulnerability to possible opposition from the defending side. Another very practically valuable scenario for the application of such a concept is a situation in which a specific attack aircraft, for one reason or another, does not have its own onboard laser target designation equipment necessary for independently targeting the laser-guided munitions it has on board, but is able to effectively use such weapons provided that external laser illumination of the target is provided by another aircraft of the group that has the appropriate necessary specialized equipment. Technically, such interaction requires extremely accurate, coordinated work of both crews involved, including precise coordination of the specific moment and duration of the required laser illumination of the target relative to the moment of the actual release of the guided munition by another aircraft, as well as the mandatory match of the special laser radiation encoding frequency code used by the target designator aircraft with the code to which the homing head of the specific guided munition used is configured, which requires accurate coordination of this technical parameter between the crews of both aircraft involved in such a joint operation at the stage of preliminary planning of a specific combat mission. Such a concept of flexible, tactically adaptive distribution of target designation functions and direct use of weapons between different aircraft of a single tactical group clearly demonstrates the general principal characteristic of modern military aviation of the most effective use of the entire set of available technical capabilities of the entire group as a whole, instead of the rigid, inflexible requirement of the mandatory presence of a full range of all necessary technical capabilities on board each individual, isolated operating aircraft, which significantly increases the overall tactical flexibility and effectiveness of the joint combat use of modern tactical aviation. Every detail, every technical solution, every professional tradition that we have examined continues to confirm the same fundamental idea. Behind the impressive appearance of a modern combat aircraft there is invariably a colossal amount of engineering thought, practical experience, and human ingenuity, much of which remains hidden from the eyes of an outside observer, but on which, nevertheless, the real effectiveness and safety of modern military aviation most directly depends.